Hello, and welcome to this introductory physics lecture on electric flux and Gauss's law. We have a few objectives here and basically one equation, Gauss's law. We want to understand what is meant by the term electric flux. We want to define it. We want to use the idea of electric flux to understand that the total flux through any enclosed volume is zero if that volume has no net charge inside of it. And we want to realize that a Gaussian surface can be used to find the charge enclosed in that surface. Okay? All right, so let's go ahead and define electric flux. It is the electric field passing through a cross-sectional area. So it's field multiplied by area, because it's just field over that area. All right? It is represented by the uppercase phi, all right? And with units of newtons per coulomb square meters. And the reason is because newtons per coulomb is one way to express electric field. And then we just multiplied it by area, which of course is square meters. Okay, so that's what it is. It's just field multiplied by area. All right. Now a Gaussian surface is where the flux is located. Because the flux has to be over some area, we call that area the surface, and we call it the Gaussian surface because it's Gauss's law. It is an imaginary surface that encloses charge. Okay. Well, I really should say can't enclose charge, because definitively, as was mentioned here in our objectives, we can look at some surface that is closed but doesn't enclose anything. Okay, so maybe that could start to make sense to you. We also want to consider that a Gaussian surface is used to calculate the charge enclosed inside, even when potentially that charge enclosed inside is zero. Okay, I guess I would say Q equals 0 coulombs. All right, now charge distribution is just a specific location of charges. When we've had three charges that compose an equilateral triangle and we're interested in the electric field or the voltage around that arrangement of three charges, that would be a charge distribution. But with millions or millions of individual charges, there are some key characteristics. The one we care about the most is that for any conductor, like a metal sphere, and that's kind of a go-to example here, just like a conducting metal ball, all the free charge will be on the surface of the object. Now, can you imagine why that would be? Why would all the free charge be on the surface of our sphere? Okay, it's a metal sphere, because all those electrons would be able to be furthest away from each other if they're on the surface. That's naturally where they would, as they push away from each other, that's their natural location, where they can all be as far away from each other as possible because they would be repelled from each other. These are free electrons. Since they're free to move, they distribute on the surface. A neat idea. Okay? All right, let's look at our one equation in two forms. Okay, so here it is, electric flux. Okay, we basically always use uppercase phi for flux because there's also magnetic flux. Okay, and there's even like flux in terms of water flow, you would still use this same letter usually. Okay, so here it is. We're saying it's equal to E times A. So that's electric field and area. All right, here's a picture of electric flux. Right, here we have an area like so. Now this is not an enclosed area. You might be thinking, wait, there's a big deal about having these enclosed areas, and you drew a sphere. Well, that's if you want to calculate the charge inside. Okay, you can have flux through any area, even a sheet like this. So this is like a rectangular sheet. The idea that we care about here is that this formula, simply E times A, is true numerically if the electric field is perpendicular to the area. Okay, then it is simply the product of field strength times magnitude of the area. Okay, but on the other hand, here's the labels. On the other hand, you can have an electric flux with a field direction that is not exactly perpendicular to the area, and we have to consider the angle between the normal vector of the area and the area. Okay, so here's the picture. All right, so here we have a Gaussian surface, right? Just not a enclosed one. We have an electric field that is at some angle to the normal direction of the area, the normal vector, and then cosine of that angle will give us the magnitude of the electric flux. So of course, if theta is 0, then we just get back to E times A for the value of the electric flux. On the other hand, if theta is 90 degrees, Well, now there's actually no field passing through the surface, thus there's no flux by definition. The field would just skim along the surface, and that would give us an electric flux of 0. Okay? Okay. All right. So here's our next way to look at electric flux. Well, electric flux is equal to the enclosed charge divided by the permittivity constant. Okay? So permittivity constant is this. Now, this might not be immediately like relevant why. It might not be immediately obvious why this is the case from what we're talking about. But an argument can be made that if I do have some charge located somewhere, and then I consider a surface around it, like the sphere we mentioned before, well, if this is a positive charge, then there's going to be a bunch of field lines that pass out of this sphere. And depending on the size of the sphere and the strength of the field, we can calculate what must have been inside. There has to be a direct relationship there, because any charge that's in there will make itself known. And if we choose a different size surface, then of course we'll have a proportionally different electric field, but the flux will be directly related to the enclosed charge. Here, that's the argument, not a proof, okay? But that is the case. This is in fact the case. This is one of the cornerstones of electricity and magnetism, this equation. It's one of the Maxwell equations, okay? Which is all of electricity and magnetism. They're governing equations. And this is the first one, okay? All right, well, in these, this is basically, this is the definition of flux. This is actually Gauss's law, because Gauss's law states the relationship between flux and enclosed charge. Whereas, again, this top equation is just the definition of flux, okay? All right, Gauss's law, okay? All right. Well, let's take a look at our examples. We just have a couple of them. This section is not heavy on the actual problem-solving side, the actual computation side of problems. The ones we do are pretty straightforward. Any ones that wouldn't be straightforward beyond the scope of the class. And so this isn't a place where we're going to see a lot of the problems that would show up on an exam, for example. This is just an important concept. And again, as I made a big deal about, it's part of this kind of broad scope look at electricity and magnetism. So it's a good thing to cover, and it's in your textbook. Okay. So example 1, the field just outside a 3.5 centimeter radius metal ball is, well, 375 newtons per coulomb, weak field actually, and points towards the ball, okay? So the direction of the field is going inwards, pointing inwards. How many electrons reside on the surface of the ball? Okay, so just outside. So what's the picture here? Well, the idea is there's a conducting ball, a metal ball of subsurface, of some type, and then we're considering a surface that here is drawn, kind of some distance larger, right? This pink surface, which you want to imagine is three-dimensional, so encompassing the entire sphere. But the idea is it's just outside it, okay? So the radius of the Gaussian surface is exactly equal to the radius of the ball, right? It's just immediately outside of it. So we're going to use definition of flux, and we see that all of the electric field lines are all going to be exactly perpendicular to the surface, because they're both spherically oriented in terms of their angle, okay? All right. So that means that our definition of flux then is just going to be the electric field times the surface area of a sphere with the radius given, okay? So what I've done here is replace A with the surface area of a sphere formula, okay? And then going to Gauss's law, the relationship between the electric flux and the enclosed charge is just going to be the following, which means if we replace the flux with electric field times surface area of a sphere, then we can go ahead and solve for Q, okay? Because we have a known radius, we have a constant of the universe, all right? And we have a known field strength, okay? Because we're given the field strength at the surface of the ball. So there we go. We find out that there are 5.1 times 10 to the negative 11 coulombs worth of electrons. Now, I actually didn't divide by 1.6 because we have to divide this by 1.60 times 10 to the negative 19, and that's electrons per coulomb. Okay, if we were to do that conversion, then this actually gives us the number of electrons. Okay, but I just left it in terms of charge. It's 51 picocoulombs, however many electrons that is. Okay, all right. So there's example 1. Let's take a look at another one. This one's not going to be a sphere. This one's going to be a conductor. Okay, those two side-by-side conducting plates. And this one's going to be, well, I said conductor, but this is going to be a parallel plate capacitor, which is two side-by-side conducting plates. All right, here it is. All right, so think of these as two metal plates, some distance between them. We don't know what it is. We're going to consider a Gaussian surface, right? Not an enclosed one, just a Gaussian surface. It's just a pink sheet like so, okay? And it's going to have a surface area that is exactly equal to the plate surface area, okay? Excuse me. And here we have here we have Gauss's law, electric flux, all right? Enclosed charge, right? I think it's enclosed, then include the subscript. We're just going to replace electric flux with E times A, right? We don't need the 4 pi r squared or anything here, because here our A is just the area of, well, some rectangle or square for that matter, but we know it precisely, okay? And now note, okay, because this is a very simple result, right? It's like, oh, okay, great, we're done. But note, Gauss's law can show that for a capacitor, the electric field between the plates is just equal to sigma over epsilon naught. Now, what is sigma? This is charge density, okay? Charge density is coulombs per square meter, okay? That's what it is. That's what sigma represents. And this, of course, is permittivity constant, okay? Well, how do we know that? Well, this is where we get it, right? Because if I just take E and I divide both sides by A, well, that side by A, right? Divide this side by A as well, then I have that the electric field is Q over A times the reciprocal of the permittivity constant. Well, Q over A, by definition, is sigma. It's charge per area, right? Coulombs per square meter. So there's where that relationship comes from. Because otherwise, it's actually hard to arrive at this relationship, to be confident that the electric field is related directly to the charge density this way. But Gauss's law allows for that connection to be made. Okay. Well, we have the third and most complex example, all right, just has a little bit more to it. And it's very much a fundamental example. That if you were to do an example on Gauss's law, this would be it, okay? So consider a conducting spherical shell. You know what? Hold on. We need to go to the next page on this one because we don't have enough space. Okay, oh, there's the actual value of the enclosed charge, okay? All right. So I had to rewrite this one on the next page. So here it is, example 3. Consider a conducting spherical shell on radius r, so that's the radius of the shell, all right? And net charge plus q, okay? So we have a spherical shell. You might be like, wait, is this a Gaussian shell? No, actually, it's just, instead of a solid metal ball, it's just a hollow metal ball, okay? What is the electric field inside of the shell, okay? All right, let's take a look at that. So here is our conducting shell. The pink surface is inside of the actual metal shell, and that's the Gaussian surface, right? Pink for Gaussian surface. So since all the charge is distributed on the outside of the shell, well, then the flux would be enclosed charge divided by permittivity, okay? And of course, we could replace flux by definition as E times A, because well, there actually aren't any electric field lines, but if there were, they would all be perpendicular to the surface. But the thing is, there's no enclosed charge, because all the charge is on the outside of the sphere, and we drew our Gaussian surface to be smaller than the sphere, so it's inside. It's not enclosing any charge, 0. That means the electric field has to be 0. Now you might reason out that inside of something like this, all the electric field lines would essentially cancel out. So that means that at any given point, they'd have to be 0. But that'd be a really difficult thing to prove, right? Gauss's law sets up that law, or this type of relationship, it establishes it. All right, and note, at the surface, the electric field at the surface is going to be the electrostatic constant. And by the way, good connection here, the electrostatic constant is 1 over 4 pi times epsilon naught, where epsilon naught is the constant that we've been using primarily of Gauss's law. Whereas when we use Coulomb's law, we use primarily this constant. Well, you can see that one constant is dependent on another. The permittivity constant is the more fundamental one, and this is just the convenient one for using Gauss's law, okay? So good thing to note there. And of course, I do make that substitution, okay? So the electric field at the surface is, to go over here, 1 over 4 pi times the permittivity constant times the enclosed charge, and then divided by the radius of the surface, or the radius of the sphere for that matter, the shell, okay? Because at that point, you'd be right along the surface as in example 1, okay? And then that would be your electric field, and it'd be related to the entire charge enclosed. Okay, so part B, what is the electric field outside the shell at a distance of 2r? Okay, because the electric field should be weaker, right? It should be. We know the enclosed charge here. We're just calculating the electric sphere, or the electric field further away. Okay, so let's take a look at what it looks like. All right, so then we'd have flux times enclosed charge, or equal to enclosed charge over permittivity, all right? The electric field is not equal to 0 since the enclosed charge is non-zero. There is, in fact, enclosed charge, okay? So then we'll just move this term from the left-hand side of Gauss's law to the right-hand side, all right? Get an expression like so, all right? And then replace A with the surface area of the Gaussian surface, which in this case is 2r squared, because essentially the radius of the Gaussian surface, we'll call it little r, and little r, of course, is equal to 2r. Little r is like the variable, because we could choose any size surface, and then big R is the fixed value of the actual physical metal shell, okay? So all I've done is replace little r with 2r. Remember to square it, which means we're gonna get a 4 here. So we get 1/16 this amount, okay? And then this, you can tell, is exactly going to be equal to, well, I mean, I guess here it's gonna be, if I factor out the 4, then I'd have this expression, the electric field at the surface, right? Well, then what's the relationship between 16 and 4? Well, of course, 16 divided by 4 is 4. So that means that this electric field is 1/4 as strong, okay? It's 1/4 as strong as the field at the surface. But we haven't gone 4 times as way, of course. We've gone twice as far. And that's because the electric field has fallen off as a 1 over r squared strength. We already know this because we know how to do the electric field of a point charge. It's just Ke and then times Q, or enclosed charge, big Q, if you will, over r squared, right? That's the electric field of a point charge. And that's, in fact, all this is. It turns out that the shell isn't behaving any differently than a point charge, okay? So nothing new, but now let's look at part C, which does have something new, okay? And so here's the 1 over r squared relationship, okay, that we expect for electric field for point charges and also for spherical distributions of charge, okay? But now we're going to consider an insulator, okay? So if the conducting shell is replaced with a sphere that has a net charge of Q uniformly distributed throughout its volume, so not on its surface, how is that possible? Because the rule said it has to distribute on the surface. Well, it doesn't have to for a insulator, all right? All right, so that's the thing. You know, I say with a sphere, but it's an insulating sphere. It could be a partial insulator, right, like a semiconductor, but it needs to be something that allows for the distribution of charge, okay? And now we're interested in the electric field 1/2 the way from the center, so kind of inside of it, okay? But it's not going to be 0 this time because it's not a shell anymore. There is, in fact, charge distributed inside. But how much charge? Because the idea is that the charge is uniformly distributed. That's a really interesting idea. So there's charge all throughout it. There's some on the surface, but there's some in the middle too, okay? So the enclosed charge is going to be equal to the proportion of the enclosed volume over the total volume, that's the total volume, V, times the total charge. Well, that makes sense. Of course that makes sense. It's a ratio. So then we use the formula for the volume of a sphere, 4/3 pi r cubed, all right? So then the enclosed is 1/2 big R, because it's half, you know, because the sphere is 1/2, the Gaussian surface is halfway inside, and there's the total volume for the total sphere, right? There's the ratio times the total charge, all right? So you get 1/8 the charge. That's really interesting, but that makes sense, right? Because there's, you know, this outside part actually has more volume to it, right? Once you get halfway in, there's not that much left. The core is much smaller. The upper layers account for more total volume. So then, using Gauss's law, this is Q enclosed, okay? That's, you know, by definition, the denominator of Gauss's law is, of course, the area of the Gaussian surface times epsilon naught, right? Well, the area of the Gaussian surface is the surface, I almost said volume, but the surface area of a sphere, 4 pi 1/2 r, again, because it's halfway in, squared. All right, so then here's a relationship. We get 1/2 times this, all right? So that's half the electric field strength at the surface, right? Because look, 1/2, look at the electric field strength at the surface, 1/4, all right? So which one's bigger, right? Well, we see, right, that this one here, right, is half the size of that one. See it? Okay. So half the field strength, okay? Well, what does that tell us, right? Well, that tells us that it didn't fall off as fast. It didn't fall off with a 1 over r squared. We went halfway in and we got half the field. Well, that's interesting, right? What does that tell us? Like, how do we, you know, piece that apart? Well, what it tells us is that there actually is a linear decrease of electric field for this unique case of when the charge is uniformly distributed over a insulator, okay? So it's a real special case. And we wouldn't have been able to come up with this based on the formulas that we had for the electric field outside of a point charge, because there's no going inside of a point charge. Now we've actually gone inside of a perfectly distributed cloud, a spherical cloud of charge. So we have a whole different proportionality. And then this leads us to the very interesting graph that for insulators, because by the way, we could take this insulator, consider a Gaussian surface that's outside, just like this one. In other words, replace this shell with an insulator, however you want to think about it. And you know what result we would get? Just like a point charge. It would just go back to being a point charge, as long as it's uniformly distributed, okay? But that means that outside we have the typical 1 over r squared relationship between electric field and distance from the center of the sphere. But inside the sphere, okay, the sphere with the uniformly distributed charge, it falls off linearly, as we can see here, okay? So we can see right here, so we can see this result, okay? And that means that it's going to go down to 0 at the center, which makes sense because when you get down to 0, there's nothing enclosed anymore. There's no space left. But it's a linear, then increase from the center back to the surface, and a 1 over r squared decrease. So we get this very interesting graph. Half linear, right? Point of sudden change, and then new function, 1 over r squared. All right, little discontinuity right there. Well, I hope this introduction to Gauss's law, one of the big ideas in electricity and magnetism, has been informative. And thank you so much for watching this video.